Let's take a look at acceleration in terms of circular motion. So acceleration is really the change in velocity over the change in time. So in the linear sense, let's have some initial velocity and its vector is this long. My final velocity would be this long. So my change in velocity is here. So here my change in velocity is in the same direction. We call this speeding up. But what about the other way? So let's take let's use a different color because I have lots of crayons. So now some initial velocity is this long, and now my final velocity is this long. My change this time is from here to here. Here's my change in velocity. So now this is slowing down. So you can see that when my acceleration and my velocities line up, I'm speeding up. When my accelerations and my velocities are in the opposite directions, I'm slowing down. But what happens when they're at different angles to each other? So, I'm sorry, they're at an angle, at some theta. What do we call that? We call that turning. So let's take an example. Here's my car. Oops, you can't see. Here's my car, and he's making a turn. He's starting up like this, and he's going around like that. Instantaneously, he has some velocity in some direction, but now he's going to turn. Let's put him at some radius r. All right. So he's going to have some initial velocity here, and he's moving this way. But now I'm going to want him to turn, and he's going to turn like this. So he's going to sweep through some angle. Let's make it theta. All right. So let's see here. He was here. Now he's going to sweep through and go end up over here. So let's have my little, let's see here. I did. All right. So right to there. So now he didn't, his velocity is the same length. All right. Because his speed didn't change. However, he swept through some angle theta. And he went some distance. Let's use a different distance color for distance. So he went this distance, this arc length, we'll call it D. All right, and maybe we'll get a little better thing. So he went R. Where did that one? Oh, here it is. All right, so he's still some distance R from the center. He swept through some angle. Here's your initial velocity. Here's your final velocity. So I kind of have a little bit of an angle here, so or a triangle. So we'll call this point A, this point B, this point C. And now I'm going to have, so we went some distance D, lowercase d. I'm going to turn this into a triangle, and for a lot of you this is going to be some sort of, all right, so I'm going to call that, we'll call it big D. All right. So big D and little d are different. D is the arc, or little d is the arc, and big D is the little triangle there. So here we go. Ready? If theta is small, like way small, how small? Small enough such that D is pretty much the same as D. All right. If theta is small, then that arc length and that chord are roughly the same. Pretty close to being the same. So now I really have two triangles. So I have triangle that's R, R, and uppercase D. So let me draw this triangle out. So I have this triangle R, R, and that length we'll call it capital D. And then I have this other triangle here. So my velocity was originally going this way. That's V initial. And then I have it's going down here. That's V final. And that's also at angle theta. All right. So now I have, what's my change? Here's my initial. Here's my final. My change, my delta V, is here. So if you don't believe that those two angles are the same, we can work this out. So this is 90 degrees. This one is parallel to this one. So if this is 90 degrees, this angle theta, and this is 90 degrees. This is 90 minus theta, so that means this one is theta. And if this one is theta, I bring this over here. This one is theta. So let's keep going. So now I have similar triangles. So because I have their isosceles triangles, V initial and V final are the same, because the speeds are the same, the radii are the same. So now the ratio of delta V over V is the same as capital D for R. This distance that it travels, because they're both functionally the same and the speed is going, that distance is the velocity times the time. So now I'm going to plug that into here. So this turns into Vt over R. So now what I have, let's keep this here. So delta V over V equals, oh, I just broke my crayon and I'm running out of time. Vt over R. So I'm going to do a little bit of magic here. Delta V over V, delta V, I'm going to put the V up there, equals V squared T over R. Put this T over here. Delta V over T equals V squared over R. Delta V over T is also known as acceleration. So this becomes the acceleration. But which way does it point? It's pointing this way. Which way is this way? Towards the center. So this is towards the center. The Greek word for that is centripetal. So this is centripetal acceleration.